section, let's understand GPIO subsystem. In this section, let's understand GPIO subsystem of Linux. First of all, let's understand what exactly is an GPIO. GPIO, which stands for General Purpose Input Output, is one of the mode of a pin of the microcontroller or of an SoC. A GPIO pin can be used for many purposes, as shown here. When the mode of a pin is in GPIO mode, it is for general use cases. So you can use that GPIO pin as an input or as an output, or you can change the mode of that GPIO pin to act as some alternate function, or you can keep that GPIO pin into another, or you can use it to receive the interrupt. So for various things you can use that pin. There are some pins of the microcontroller which cannot be used for all these purposes, like input, output, analog, etc. So those pins are just called as pins. They are not called as GPIOs. In this course, we'll be dealing with GPIOs or GPIO pins of the AM335X SoC. This AM335X SoC has 4 GPIO controllers. GPIO controller is a hardware of the SoC which controls the GPIO mode of a pin. So there are 4 GPIO controllers on this SoC, like GPIO 0 to GPIO 3, and each GPIO controller controls 32 pins. That's why the AM335X SoC gives in total 128 GPIO pins. That doesn't mean that all these 128 GPIO pins are available on the board, that is on the BeagleBone Black board. This is what the SoC offers. And on the board, you may have access to a lesser number of GPIOs. We'll see that later. If you just open the technical reference manual of this SoC, there is a section 25.1 where they have explained about the GPIOs and about the GPIO controllers of this SoC. So where you can see that it says the general purpose interface combines 4 general purpose input output modules. Each module provides 32 dedicated general purpose pins with input and output capabilities. Thus, the general purpose interface supports up to 128 pins. Let's move forward. GPIO pins are configured through memory mapped GPIO configuration registers. So in order to configure a pin, like in order to set its mode, like input, output, in order to activate its pull-up, pull-down resistors, or in order to control its output type, so you need registers, isn't it? Those are called as configuration registers. The configuration registers of GPIO controller 0 are placed at this address in the memory map of the SoC. So what this row signifies is that GPIO 0 controller has some set of registers to control its GPIO pins, and the base address of its register set is this one on the memory map of the SoC. And the GPIO 0 controller consumes around 4 kilobytes on the memory map of the SoC. That means each controller actually consumes around 4 kilobytes on the memory map of the SoC. So this is a base address of the configuration registers of GPIO 1 controller, like that. Now you can get this table on the technical reference manual of this SoC. Let's move forward. In a microcontroller or in an SoC, most of the pins have multiple functionalities, also called modes. For example, a pin of the SoC can act as a simple GPIO, or it can act as UARTX line, or UARTRX line, or MMC data line, etc. This is called pin multiplexing. Pin multiplexing helps SoC designers to produce an SoC with lesser pin counts. When a pin is used for one functionality, it cannot be used for another functionality unless you reconfigure it. This is what we call as mode setting or pad configuration. This is actually pretty much common in all microcontrollers or on all SoCs. Each pin supports multiple functionalities or functions, and each pin has got its own pin configuration register where you can configure its mode. So we'll explore more on this by going through the data sheet a little later. So in the next lecture, let's explore the BeagleBone Black's headers to understand what are all the GPIOs which are available on the BeagleBone Black hardware. For this, we have to go through the system reference manual of the BeagleBone Black hardware. So we'll see that in the next lecture. In the BeagleBone Black system reference manual, so if you go to the section 7.1, you see here expansion connectors. Actually, this board has got two expansion headers or connectors. One is P8 and another one is P9. And let's explore the connector P8. The connector P8 has got in total 46 pins. This table actually explains the expansion header P8's pinout. Now let's understand this table. First of all, there are many columns. The first column is pin number. This is a pin number of the P8 header. And the processor column, what you see here, is a name of the SoC pin, which is connected to the expansion header P8. This is name or identification number of the SoC's pin. And after that, there is a name column. So this name column is actually confusing. I'm not sure what it strictly signifies because that is actually not mentioned here. They say the processor column is the pin number on the processor, but it's not pretty much sure why this name column is used, and it is confusing. So I would suggest you to not to look into this name column. So basically what this signifies here is the SoC's pin number, which is R9, is connected to third pin of the expansion header P8. So you can get the details about this processor pin R9 on the data sheet of this SoC. Let me take you to the data sheet of this SoC. So here is the data sheet. And when you go to the data sheet, you can go to the section. There is a section called Terminal Configuration and Functions, and go to pin diagram here, pin diagram section, and select this package ZCZ, because that's a SoC packaging which is being used on our SoC. When you click that, this actually explains the pin details of the SoC in that packaging. The packaging is this one, ZCZ. So here you can get the column R. You can see it, R9. R9, here it is, R9. This is R9. So this pin of the SoC is connected to third pin of the expansion header P8. So column R and row 9. It is mentioned as GPMC underscore 86. That's a naming convention used in order to name the SoC pins. GPMC, that stands for General Purpose Memory Controller. That's the first functionality, or that's a mode 0 functionality of that pin. Here the pins are actually named according to their mode 0 functionality. When you click that, it takes you to the pin details. R9, here it is, ZCZ ball number, that is R9, and its name is this one. The reason why they have given this name is because this pin, when it is kept in mode 0, act as GPMC 86 pin, 86 functionality. The name is given according to the mode 0 functionality of the pin. Now you can see here this pin actually has got only 3 functionality. So let me zoom it. It can act as GPMC, it can act as MMC1 data line, or it can act as a GPIO. So when you keep this pin in mode 0, so this is a mode actually. When you keep that pin in mode 0, it acts as GPMC. That means that pin will be taken by the general purpose memory controller of the SoC. When it is kept in mode 1, it acts as a MMC1. And when it is mode 7, then it acts as a GPIO 1_6. Now the meaning of this is this pin will act as GPIO 1 controller's 6th pin. Basically, this pin belongs to the GPIO controller 1, like that. Now, same thing you can apply to all the pins what you see here. This table also shows the same thing. What is there in the data sheet? Mode 0, mode 1, and mode 7. So mode 2 to mode 6 are not available. This pin actually supports only 3 modes. Basically, if you check this table, what you understand is for most of the pins, when you configure the mode 2, mode 7, it acts as GPIOs. One thing you should understand here is that, whenever you configure a pin into mode 7, it acts as GPIO. So now let's explore some of the default pin configuration of the P8 and P9 headers of BeagleBone Black hardware. This image I have taken from the beagleboard.org website, and it actually shows the functionality of the pins available on the board. So here the pins which are marked with red strips, these are actually used for power, ground and reset purposes. You cannot use them in your program. These are not modifiable or reconfigurable pins. And whatever the pins you see in this color, these are actually free pins. You can reconfigure them in your program. They are actually free. So all these pins are free. They call it as available digital. And these pins are for analog purposes. You cannot reconfigure these pins on the P9 header. These pins are used for analog applications. And whatever the pins you see in this orange color, these are reconfigurable pins. And some pins you can reconfigure and use it, and some pins you can't. For example, take a look into these pins. So these pins are already configured for MMC1 functionality. By whom? By the device tree file of the board, which is given by the beagleboard.org. When you use the default or standard device tree file, which is given by the beagleboard.org, that is AM335X boneblack.dts, that actually consumes these pins for MMC1 functionality. So MMC1 means eMMC in our board, isn't it? That's why, since eMMC is already being used, so you cannot reconfigure these pins. If you reconfigure these pins, then you will lose access to the eMMC. Don't do that. But you can reconfigure these pins. Why? Because there is no LCD on our board. So you can use these LCD pins for any other purposes. Like you can configure these pins to GPIO functionality or for any other functionality according to that by changing the modes of the pins. And as I said, these pins are totally free and they are not used by any peripherals. So you can use it for any functionalities. So on the SoC, you know that we have in total 128 digital IOs, isn't it? Or GPIOs. But on the board, you have access to 65 digital IOs. So in the next lecture, let's understand the pad configuration register. I'll see you in the next lecture. Conf. These are pad configuration registers. So now let's say I want pad configuration register for this pin. Its name is GPMC BEN1. And you can search that, okay, GPMC BEN1. Here it is. So this register you have to use in order to configure the mode for that pin. Let's explore this register. Here it is. This register is of 32 bits, and so only 6 bits are implemented actually. First 3 bits, they decide the mode because there are 8 modes. So 3 bits are required. So this is pad functional signal mux select. And the next bit, that is bit number 4, that is the bit number 3, decides pads pull up or pull down enable. So you can use this bit to enable the pull up or pull down resistors. And by using bit number 4, you can select whether you want a pull down or pull up, because most of these pins support internal pull up or pull down resistors. And after that, the bit number 5 decides the RX active status, and the bit number 6 decides the slew rate of the pin. So there are two options, fast or slow. That means what we understood from this lecture is, every pin has got its own pad configuration register, and by configuring it, you can change the mode of that pin, and you can also activate or deactivate pull up or pull down resistors. You may be wondering, what's the default mode of a pin? In this section, in the technical reference manual, they have explained it. The mux mode field in the pad control register defines the multiplexing mode applied to the pad. So you can see here, for most pads, the reset value for the mux mode field in the registers is 7. But there are some exceptions. The exceptions are pads to be used at boot time to transfer data from selected peripherals to the external flash memory. But for most of the pins, the default mode is mode 7. So please keep this in mind. Hey, welcome back to the lecture. So in the previous lecture, you understood the hardware aspects of the GPIOs, isn't it? Now in this lecture, let's see how Linux handles those hardware GPIOs. So actually it is handled by the GPIO framework of Linux. So here is a block diagram of the Linux GPIO subsystem. Basically, the whole Linux framework is divided into 3 parts. There is a central GPIO core. This is a GPIO framework or GPIO core of the Linux, which is hardware independent. So the exact file name is drivers gpio lib.c. So that's the GPIO core. And after that comes the hardware dependent part, that is the producer. That is nothing but the GPIO controller driver. This GPIO controller driver knows how to handle the hardware GPIO controllers. In the case of AM335X SoC, the GPIO controller driver you can find at this location, drivers gpio omap.c. So that's the GPIO controller driver. That driver knows how to configure the pins, how to write into the pins, how to read from the pins, how to activate the pull-up, how to deactivate the pull-up. Everything is implemented in the producer driver or GPIO controller driver. So the Linux framework doesn't know how to talk to the SoC's hardware. So what it does is, it actually forwards the request to the GPIO controller driver. And then GPIO controller driver handles the hardware GPIOs. And the third part is the consumers. Consumers are any drivers, okay, which consume the GPIOs, like a keypad driver, joystick driver, any driver. You can call it as a client driver. So the consumer's driver need not to worry about how to access the hardware GPIOs. All the consumer drivers they do is they just use the APIs which are exposed by the Linux GPIO subsystem. That's it. So it just uses that APIs, and after that request is forwarded to the GPIO controller driver. and the GPIO controller driver talks to the GPIO hardware. Okay, it's like that. So during boot up, the controller driver registers itself to the GPIO framework using GPIO registering services of the Linux GPIO subsystem. Basically, the GPIO controller is represented in Linux by the data structure GPIO chip. And apart from that, there are also some helper drivers, okay, which are available in the Linux subsystem. Again, those are hardware independent helper drivers, okay, like GPIO LED driver. The GPIO LED driver gives a generic framework or a class to handle LEDs. So basically, you see sys class LEDs in the sysfs directory. So that is actually created by the GPIO LED driver. And you also see a GPIO keys driver and also GPIO sysfs driver. So with the help of GPIO sysfs driver, you can manipulate various GPIOs of the hardware through sysfs interface. Basically, it creates a class GPIO under sysfs directory from where you can export and unexport GPIOs, and you can use some user space commands to play with hardware GPIOs. So that is actually handled by this helper driver, sysfs driver. So to conclude this, the GPIO subsystem has majorly three parts. One is the consumer driver, that means the driver you write which consumes the GPIOs of the hardware. So in this consumer driver, you don't write any code which directly talks to the GPIO of the hardware. So that is left to the controller driver. So the consumer's drivers, they just use the APIs which are, or functions which are exposed by the GPIO Linux core, okay, or framework. And after that, there comes the GPIO core, which is a hardware independent part, as I said previously. And after that, the GPIO producer. Actually, it's the GPIO controller driver, which knows how to handle the hardware GPIO controllers and the pins. Now let's understand how the consumer can access the GPIO pins. Let's understand this with an example. Let's say you have got a keypad and the keypad is connected to the board, and now you want to handle that keypad. So what you do, you write a keypad driver, right? So that keypad driver is a consumer driver. So there is a GPIO controller, let's say GPIO controller 0, which gives you 32 pins, and that is actually a producer. So this GPIO controller is handled by the GPIO controller driver. So you need not to worry about that. Out of these 32 pins, your keypad, let's say, uses 7 pins. So hence, a keypad is called as a consumer because it consumes pins. It just consumes 7 pins of the GPIO controller. And that keypad is handled by the consumer driver, that is keypad driver. So now the question is, how does the consumer driver know about those 7 pins where the keypad is connected? The consumer driver cannot hard code that details, isn't it? Why? Because the consumer driver, if it hard codes the GPIO details, then it may work on one board, but the driver cannot be used on another board. Why? Because on another board, the keypad may be connected to some other controller or to some different pins, right? So that's why the consumer driver cannot hard code the details of the GPIO pins and the controller, isn't it? Now, how do you solve this problem? So what you do is you supply that as a platform data. So that's why what you do is you write a consumer device tree node where you explain what are the GPIOs you are going to consume. So that's what we call as consumer device tree node. So you write a keypad device tree node for this use case. So that's why whenever you write a consumer driver, so there will be one consumer device tree node in the device tree file. And the consumer driver can get the details about the pins from the consumer device tree node, and then it can configure those pins. So that's how you can work upon the keypad. So that's why we have to learn now how to represent GPIOs in a consumer DT node. So in order to represent GPIO pins in the device tree node, you have to mention what's the GPIO number the consumer is going to consume. So you have to mention to which GPIO controller it belongs to and what is its hardware property, whether it is active low or active high. So you have to mention that in the device tree node. So all this information actually becomes a flat form specific data for the consumer driver, isn't it? Once there is a match between consumer device tree node and the consumer driver, the probe function executes and the consumer driver accesses the DT node to extract the information about the GPIOs used to connect the keypad and configures them. In order to encode GPIO details inside the device tree node, we use GPIO device tree property. So GPIOs being consumed are represented by function GPIOs property. So this is actually a generic form of a property where it has got two parts here. The first part signifies the function for which the GPIO is being used, and the second part is a standard name, GPIOs. So the function being the purpose of this GPIO for the consumer. You can omit this part, but that is not recommended. So instead of function GPIO, you can leave this last S letter. That is also okay, but that is not recommended. That's why the best practice is to use the form function GPIOs. So we'll see one example. So here is an example, a beautiful example I have taken from the kernel documentation, which you can get in documentation GPIO board.txt. So this is a consumer node, and you already know about this. Is a compatible property which is used to match with a compatible driver. So now here let's understand this. This is a GPIO property, and this GPIO property is used for the function LED. This is a function name. This is also called as a connection ID. And this consumer node uses a couple of GPIOs. This consumer node uses these three GPIOs of this controller for LED functionality, and it uses this GPIO of this controller for power functionality. So that's the meaning of this. So basically, the different GPIOs are segregated according to their function name. So you can see here, this property will make GPIOs 15, 16, 17 available to the driver under the LED function, and GPIO 1 as power GPIO. So now you may be wondering what kind of name it is. I mean, whether it's the standard name or how to select this function name. Now that is mentioned or documented by the driver who is going to use this consumer node. What name you should use in the place of function is documented in driver's device tree binding documentation. So all you need to do is mention the GPIO number, its controller details, and its hardware details like active high or active low, something like that. So here it is. So this is how you should write the property. First you have to mention the P handle of the GPIO controller to which this pin belongs to. So in our case we have got GPIO 0 controller 1, 2, 3, right? So one among those you have to mention here. Now the next one is a local offset to the GPIO line. So this number actually varies from 0 to 31 in our case. Why? Because each controller handles 32 pins. And this is a hardware property of the GPIO pin. Some GPIOs could be active high, some GPIOs could be active low. So all these different consumer flags you can get in DT bindings, GPIO, GPIO.h. So you can use active high, active low, open drain, open source, like that, okay? Persistent, transitory, like that. And if you are using any GPIO in open drain state, then you can use this open drain flag. So you can mention that here. So this is a function name. The driver's binding document tells you what name to use. And this is also called as connection ID. So we'll see that later, okay, why it is called as a connection ID. And so that's about writing a GPIO consumer device tree node. All right, so you will get more clarity when we do one exercise on this, okay? All right, so that's it for this lecture. And in the next lecture, let's understand some of the kernel functions to manipulate GPIOs. I'll see you in the next lecture. Let's do one exercise on GPIO. Through this exercise, we are going to understand how to use Linux GPIO subsystems APIs to handle the GPIOs of the hardware, and we'll also understand how to write a device tree node which consumes GPIOs and various other things. So we are going to write a GPIO sysfs driver. First of all, there's absolutely no need to write this driver because the GPIO sysfs driver is already available in the Linux GPIO subsystem. So it is already there actually, a GPIO lib sysfs driver. This exercise will be a custom one. That's okay, you can learn lots of things with this exercise. The goal of this exercise is to handle GPIOs of the hardware through sysfs interface. The driver should support the below functionality. The driver should create a class called Bone GPIOs under sysclass. This you can easily accomplish by using the function class create. And after that, for every detected GPIO in the device tree, the driver should create a device under sysclass Bone GPIOs. Again, you can easily do this by using device create, isn't it? Remember, for every detected GPIO in the device tree, the driver should create a device under the class what you have created in the first step. The driver should also create 3 sysfs files, or you can call it as attributes, for every GPIO device. The attribute 1 is direction. This is used to configure the GPIO's direction. You can use these possible values with this direction. It could be in or it could be out. When direction is made as input, the direction of the GPIO will be changed to input mode or output mode, like that. The attribute mode can be read and write. The attribute 2 will be value. So this is used to enquire the state of the GPIO or to write a new state or new value into the GPIO. Possible values could be 0 or 1. Basically, value you can use to read the input state or the output state. And value can also be used to write a new state into a GPIO pin which is already in output state. And after that, the third attribute you are going to create is label. This is used to enquire label of the GPIO which is read-only. That's why you have to implement the show and store method for this, show and store method for this, and show method for this. Implement all the show and store methods for the attributes. I hope you understood the exercise. The goal of this exercise is to handle the GPIOs of the hardware through sysfs interface. and let's implement this. Alright, so now let's understand the device and driver binding information. For this driver, you have to create the device tree nodes as below. You have to create device tree in the way the driver wants, okay? Because the driver writer should document how a device tree writer should create device nodes, okay, in the device tree binding documentation. So that's why for this driver, you have to create the device tree node like this. So there must be one node, okay, one device node, and it could be any name, and the compatible property must be initialized to this string, born GPIO sysfs. That must be the compatible property. So if you use any other value, then the binding will fail. So the compatible property you must use as suggested by the driver in the device tree binding documentation. And after that, inside this device tree node, you can create children. So one child node for each GPIO. For example, this child node explains one GPIO, and this explains another GPIO. Now, to explain a GPIO, you have to use two properties. The first one is a label property. So this is just to give a label for this child node, okay? And driver says it's an optional property. The device tree writer can ignore this suggestion. But this driver says that there must be GPIO property. This is a mandatory property. And when you write a GPIO property, the function name must be born. And after that, this GPIO property is initialized to a GPIO pin. So here this is a pin number, and this is a controller to which this pin belongs to. Basically, it's a P handle of the controller. And after that, this is a hardware property of the pin. So like that, you have to explain your GPIO. So like this, you can create as many nodes you wish. So if you want to include 10 GPIOs, then there should be 10 child nodes, okay? One for each GPIO pin. Now let's start doing this exercise, and first we'll create the device tree, and later we can code for the driver. I'll see you in the next lecture. Alright, so now let's create one folder for this exercise. Let me create 007 GPIO sysfs. So now first let me just copy a make file from my previous exercise. Okay. And after that, let me just create the source file. I would call it as GPIO sysfs.c. Okay. Alright, now let me open the make file. So GPIO sysfs.o. I'll just remove this line. Okay, it's not required. Now this is our driver source file, and here now you have to implement the init function, the cleanup function, implement the probe function, implement the remove function, and also write a code to register the platform driver. So because this will be registered as a platform driver, so all these things you have to implement now. So I have just copied few header files here. These header files I just copied from my previous project. We'll see whether we need any more GPIO related header files or not. Okay, we'll see that later. And after that, this is a macro I copied from the previous project. So these are some macros which explains the project. And after that, the important part is this one. I'll be using these data structures, so which is very similar to the previous exercise. In the previous exercise, we used PCDev private data, right? So I just changed the name to GPIO dev private data. So this is used to hold a private data related to a GPIO pin. You can keep any information related to a GPIO, but for the time being, I just store the label of the GPIO pin. So I consider that as a private data of a GPIO pin. We'll see later whether we need to include more information in this structure or not, okay? And after that, this is a driver private data structure. So in the earlier exercise, we used PCDRV underscore private data. So I just changed that to GPIO DRV underscore private data. So for a time being, it just stores the total devices or total GPIO pins which are detected in the device tree. And this is to hold the class pointer. That's it, okay? And after that, let me just create one variable of driver private data structure. So GPIO DRV private data. I'll just write GPIO DRV data. All right, now let's implement the init function first. So this is our init function, GPIO sysfs underscore init. And in the init function, first I'm going to create a class called Bone GPIOs. Okay, so this is as per the exercise. And after that, we have to register our driver as a platform driver, isn't it? All right, so for that, let's create a structure, struct platform driver. So I would call it as GPIO sysfs platform driver. So let's initialize this. And let's initialize that later. So we are going to register this platform driver in the init function, platform driver register, right? Ampersand GPIO sysfs platform driver. That's correct. And after that, let's initialize this probe. I would call it as GPIO sysfs probe, and remove function, remove is equal to GPIO sysfs remove. And after that, you have to initialize the driver member element of the structure struct platform driver. So driver is equal to, first of all, you have to initialize the name is equal to, I would call it as bone GPIO sysfs, and after that the match table. So for this exercise, we are going to use only device tree based device instantiation, okay? So that's why it is enough if you just initialize this device tree match table. Match table is equal to, before initializing this, let's create a of device ID, struct of device ID. So I would just call it as GPIO device match, something like that. Basically, as you know, it's an array is equal to, so the compatible property. So here you must give the compatible devices list, isn't it? So let's initialize compatible is equal to org. So you must use bone GPIO sysfs, okay? Bone GPIO sysfs. And after that, this must be a null terminated string. So that's why you have to give a null entry here. All right, so here you can initialize that of match ptr of GPIO device match. That's it. All right, so now let's implement the cleanup function. Cleanup function will be, void exit GPIO sysfs exit void, so class destroy drv data dot class GPIO. So after that you just have to do platform driver unregister. So now let's implement the probe function. I will implement that about this, okay, and I will implement that here. So probe function GPIO sysfs probe, so it takes struct platform device pdev, right? So for a time being let's return 0, okay, and after that the remove function remove, okay, return 0. So that's it. And now let's compile this code and let's see what happens, okay. Make host. There seems to be some problem. Okay, so there is a spelling mistake actually. Right here. Okay. All right, so also there is one more mistake here. Okay, so this is match table. Right, so it compiles fine and complete up to here. I'll see you in the next lecture. So now in the previous lecture we implemented init and exit functions. Before implementing probe and remove functions, now let's first implement the device tree nodes for this driver. Now for that I'm going to save and exit this, and now let's open our .dtsi file in order to create device tree nodes. So let me go to the Linux path arch boot dts, and here we should open am335x bone black / ldd course.dtsi. So here we have a couple of entries which are related to our previous exercise, so let's keep them, need not to remove them. Okay, now let's create a new device tree node for our driver. I would call it as bone GPIO devs, okay, and let's create the node. Now this device node is compatible with the compatible string which is hosted by the driver. So first let's create a compatible property. Compatible is equal to, so here the value must be as suggested by the driver's compatible list, right? And we have to use bone GPIO sysfs. Actually it is org comma bone GPIO sysfs. Now let's create child nodes. So let me create the first child node. Let me call it as GPIO1. So this is a child node. So this explains one GPIO. Okay, so like that let me create 5 GPIO child nodes. Okay, let me copy this. So let me just align this. Right, so I just created 5 child nodes, and let me call it as GPIO2, GPIO3. Alright, so let's make it as GPIO4, and this is GPIO5. And here we should use the property label, a label property. So label property is used to give a label to a node. Okay, it has got nothing to do with GPIO, so that the driver can read it. So now before writing the label, let's understand what are all the GPIOs we are going to use for this exercise. Okay, we cannot use any random GPIOs, isn't it? So we have to use those GPIOs which can be tested from our BeagleBone Black hardware, right? So it must be available. on our expansion header. So that's why let's check the expansion header once again. Now here you see there are various pins which are already shared for some other functionality. For example, you cannot use MMC1 pins here because there is a eMMC which is consuming it, right? These are available digital pins, so you can make use of this, or you can make use of any LCD pins. Since LCD is not connected, you can use them. But in your setup, if LCD is connected, in that case you may not use those pins. Okay, now let's do one thing. So let's use these three pins. Okay, GPIO 66, 67 and 68. So here it is just written that GPIO 66, right? But we are not sure to which GPIO controller this pin belongs to. So for that we have to explore the system reference manual. So basically I'll be using a P8's 7, 8 and 10 pins. Okay, so now let's go to the reference manual. So in the reference manual, go to the section expansion connectors. Okay, right here and here. So 7, 8 and 10. Okay, 7, so which is this line. So we are going to use the second pin of GPIO controller 2. So let's do that. So we'll use that as a label. Okay, so label is GPIO 2.2. So this GPIO node explains second pin of the GPIO controller 2. Okay, like that. And after that 7, 8. So the 8th pin of this expansion connector is GPIO 2.3. So let's create a label in the next node 3. Okay, all right. Now for these two nodes, okay, I'm going to use those GPIOs which are currently connected to the onboard LEDs of the BeagleBone Black hardware, because we can test our driver by working with onboard LEDs. Otherwise you may have to connect some external LEDs to these GPIOs. So instead of that, we can make use of the onboard LEDs. Now let's explore to which GPIO pins the onboard LEDs are connected. You can again go to the system reference manual and just search LEDs, user LEDs. Here it is, and you see here, so there are 4 user LEDs. For our exercise we can make use of these 2 LEDs. Okay, GPIO 121 and GPIO 222. I'm going to this node here. Now I'm going to give label is equal to, I'll just write user LED 0 and colon GPIO 121. Okay, and for this I'm going to use user LED 1 GPIO 222. That's it. Alright, so after that we have to create the GPIO property. So you have to use function name hyphen GPIOs. Okay, so the function name must be bone for this driver, and you have to mention the GPIO controller, the pin number and the hardware property of that pin, so which we call as GPIO flag. So now let's do this. So now let me go here, bone GPIOs is equal to angle brackets. So the first entry should be the P handle to the GPIO controller. So GPIO controller in this case is GPIO 2. So let's give ampersand GPIO 2. Pin number is 2 and the flag is GPIO active high. Now if you're wondering how did I get this name GPIO 2, okay, so you can check in the SOC level DTSI file. because GPIO controllers are on-chip peripherals of the SoC, isn't it? So that's why you should find this entry in the SoC level DTSI file. For example, let me just quit this. So let me go inside Arch ARM boot DTS. Just open AM33XX L4.DTSI. Search for GPIO 0. Here it is. So this is a node for the GPIO controller 0. And after that, GPIO 1. So this is a node for the GPIO controller 1, like that. Okay, it starts from GPIO controller 0. Fine. So now let me just copy and paste this line for the second node, for the third node as well, fourth node, okay, and for the fifth node. So let's just change here. This is GPIO 2 22. This is GPIO 1 21. This is GPIO 2 4, and this is GPIO 2 3, like that. Okay, so please note that there is no comma after these entries. Alright, so we just created a couple of child nodes, and now let's terminate each and every node with semicolon. Okay, so we forgot to do that. You have to terminate with semicolon, and here as well. Okay, the Bone GPIO devs, so this is a parent node, and you should also terminate that. So that looks good. And now let's save and exit, and now let's first try to compile this. Okay, so let's use the command make arch is equal to arm cross compile, and you have to use the name of the DTB. So let's run this, and it's fine. Okay, so the device tree compilation was fine. So now we actually finished writing our device tree nodes for this driver, and in the next lecture let's continue GPIO sysfs driver coding. So we will implement probe and remove methods. Okay, I'll see you in the next lecture. Hey, welcome back to the lecture. So in this lecture, let's implement the probe function. So now in the probe function, we are going to process the device tree nodes, and we are going to configure the hardware, and the hardware in this case is GPIO pins, isn't it? Now here we should note that we don't know how many child nodes are there in the device tree. The driver doesn't know that information. In the device tree file, we have one parent node, and under that parent node we have a couple of child nodes, isn't it? So the driver doesn't know how many child nodes are there. So then the question is, how does the driver process? So that's why the driver has to query a child node, okay, in a loop until it processes all the child nodes of a device tree node. So you have to implement some kind of looping. So the function to do such things is already available in the Linux kernel. Now let's go back and check the device tree processing functions in the Linux kernel. Let me take you back to the Linux, include Linux of.h. Okay, so of.h right here. So I actually showed you this header file in the previous videos as well. In this file you get a lot of kernel functions to process the device tree nodes, isn't it? Here just search for each child. So here's a macro for each child of a node. That suits our requirement actually. Or for each available child of a node. So the difference between these two is the available child of a node, it actually invokes this function get next available child. So if you just check that, so you can see that here what this function does. It skips any disabled nodes. When you make status is equal to disabled, a node is disabled. So this function doesn't query a node whose status is disabled. So that's why I think for our driver, this function suits for each available child of a node. And here you just mention the detected parent, and child will be populated by these helper functions. Let's see. So you just have to give the parent device node. So the parent will be of type struct device node, and it returns you the child device node. I hope you get the idea. So if you want more information, so just go through this, okay, see how these functions are implemented. So now let's go back to the proof functions. So here I just copy this. For each available child of a node, parent and child, and it's a loop. So now let's create the parent struct device node parent is equal to, so how do you get the parent? pdev, right? So how do you get the parent device node? So parent device node you can extract from here. So let's again explore the platform device, because it is very hard to remember all these things. So let's check the platform device. So let's go to platform device.h right here. So platform device has dev, okay. So pdev of dev, okay, and after that device has it should have device node, isn't it? So here it is, device has device node. So this is a parent device node, okay. So dev dot operator of node, okay. So this is a parent. So this is parent device node, and after that child struct device node child is equal to, oh sorry about that, so here it must be a pointer, okay, right. So child, so just make it as null, because this will be populated by this macro, okay. So now if you just check this macro for each available child of node, basically it's a C macro which is going to be replaced by this for loop. Basically this is going to be replaced by the for loop, and inside the for loop it calls this function get next available child. So if this function returns null, then this for loop breaks, because there is a null check actually. So that means if you are inside this loop, you have successfully obtained one child. So now first what we'll do inside this loop is, let's allocate a memory for our device private data. So what is our device? Struct GPIO dev private data. So I will just write dev data. So I just create a pointer here, and let's allocate the memory dev data is equal to, so dev m, since we have used the dev m version, you have to use dev here. So we don't have dev, let's create that. Struct device dev is equal to pdev of dev. You should mention the ampersand here. All right, so after that I just implement the error checking here. Now we have to query the child nodes, and we should populate our GPIO dev private data. So basically there is only one information to fill up in this variable, that is actually the label. So now let's first query for the label. Okay, label is nothing but a string data, isn't it? So how do you read device tree string property? You can just search for read underscore string. So of property read string, you can use this. Let's check this once again. All you need to do is you have to mention the device node which is detected. So actually we have to mention the child. So child device node you have to mention here, and the property name is label, and you have to give one placeholder. This is a pointer to null terminated return string, and this function actually returns 0 on success, otherwise an error code. So let's use this. First you have to give the device node of the child, so that is child, and after that the property name is label, comma, after that a placeholder, address to a placeholder. So now let me create a variable here of type char star. Okay, char star name, something like that. So this is a placeholder. So what I do now is I just send the address of this. So address of name. Okay, and if the return is non-zero, then there is a problem. The error could be because of multiple reasons. It could be because of property doesn't exist, or if the property doesn't have any value. All those cases will result in error. Okay, so if you are wondering why did I use ampersand of name but not just name, that's because this function demands that. So you can see this function once again. So here what it needs is const char, a double pointer. So that's the reason why I'm sending address of this pointer. We have to make this as a const char. So now it's fine. And you see here at this line, it just hooks up the properties value into our pointer. That's it. If the return value is non-zero, okay, so then that means something went wrong. So that's why we'll just print here dev1. So in that case we'll use some default value, okay, for the label. I'm going to use some default value, and I'm going to initialize this dev data's label field. Let me use sn printf for that. Sn printf dev underscore data of label. Let's mention the size here, size of dev data of label. Now we'll use some default label name. I'll just write unknown GPIO %d and comma I. Right, so we'll declare the I variable later. So this formatted string will be copied into the label field of the GPIO private data. Okay, so that's how we initialize it. So else we can just do string copy to dev data label field from this name. Okay, so the query was successful. So you can just copy from here to here. Okay, and let's just print dev info GPIO label is equal to %s/n dev data of label. We just did a query for the label field of a child node, and we saved that in the device private data. Alright, so now the next query will be for the GPIOs which are present in the child nodes. So I will cover that in the next lecture. Before that, let's compile this to see whether there are any errors or not. Okay, so first of all, I have used a variable I here, so let me just declare that. and let me do I++ at the end. Now let me save and exit this, and let me do just make host. It builds fine, no problem. Let me do make, and it builds fine. Great. So complete up to here, and I'll see you in the next lecture. Alright, now let's continue coding. So far we have implemented this code block, which is used to read the value of the label property in the device tree node, isn't it? So now our next task is to read this GPIO property. Now how to read this property from the consumer driver? So for that we have to explore acquiring and disposing a GPIO from the consumer driver. To acquire a GPIO, you can use this function gpiod_get. This is a kernel function which is exposed by the GPIO subsystem of Linux. Now all these are functions which can be used by the consumer driver. So that's why in order to use these kernel functions, you have to include the header file consumer.h. So to acquire, you use gpio_get, and it returns a GPIO descriptor for the acquired GPIO of the system. And by using this GPIO descriptor, you can handle that GPIO. You can see here you have to mention the connection ID. So this connection ID is nothing but the function name what you have used while writing the GPIO property. So here bone is a function name. From the consumer driver point of view, that's actually a connection ID. Now let's explore this kernel function. Alright, so now as I said, you have to include consumer.h. Okay, so go to Linux, include, in the include go under Linux, and here go under GPIO and consumer.h. Here it is. So you have to include this header file. Here you see various functions to deal with the GPIO of the system. Just search for gpiod_get. Right, here it is. This is gpio_get. This is actually implemented in gpio_lib.c. So gpio_lib.c is a Linux GPIO subsystem code. Here you see gpio_get, and it takes all these arguments. Now let's understand. First of all, the first argument is a pointer to a struct device. This is a GPIO consumer, a consumer device. So here you have to mention the detected device, so which you have got in the pro function. And after that, next is a connection ID. It's a function within the GPIO consumer, and here it's a optional flags. So now let's explore this flags, gpiod_flags. Flags you can find in consumer.h. So here it is. These are the flags. So one among these values you can use that. It could be gpiod as is. That means when you use that gpio_get function, the GPIO's behavior will not be modified. It will be retained as it is. So if you use gpio_in, then that GPIO will be configured in input mode. So like that, you can use one among these flags. Now after that, if you want to dispose or free that GPIO, then you can use gpiod_put. So usually we use gpiod_get in the pro function, and we use gpiod_put in the remove function. But you need not to use GPIOD underscore put. Why? Because there is also device managed variants are available. So that is devm underscore GPIOD underscore get. So you can check that in the consumer.h file. Just search for devm underscore. So you can find the implementation of this function in GPIO lib-devres.c. Here just search for devm underscore GPIOD get. Here you can see that this is a resource managed version of GPIOD underscore get. But for our exercise, we cannot use GPIOD underscore get because we are working with child nodes, isn't it? That's why we don't have pointer to this struct device. So what's happening in our code? In our code, in the loop, we actually obtain the child, isn't it? A child is of type struct device node. Okay, so that's why we cannot use this function. Okay, so that's why to obtain a GPIO from a child, there is a separate kernel function which is given by the consumer.h. So a little different, a variant of this function. So now let's explore that. So just go to the consumer.h and here you find a function called devm firmware node get GPIOD from child. So here this is a detected device, connection ID, and here you must mention the handle to the child. So a handle is of type struct firmware node handle. So in the program what we have is pointer to struct device node, isn't it? Let's check this struct device node. Struct device node is there in of.h. So struct device node, and it has got firmware node member element here. So you can use the pointer to this variable here. That's a child's firmware handle, and after that optional GPIO flag, and you can give any label for that detected GPIO. This label will be used to initialize a label field of the obtained GPIO descriptor. So this GPIO descriptor has got a label field here. So that label will be used to initialize this field, okay, in the GPIO descriptor. Remember that whenever you use GPIOD underscore get function or any of its variants, okay, you get an object to the struct GPIO underscore descriptor. All right, now let's go back to the program and let's continue our coding. So after this, let's use this kernel function devm underscore firmware node get GPIOD from child. I'm going to copy this and let me take that into my program, and this function returns a pointer to the struct GPIO descriptor. So we have to create a pointer variable to this structure now, right? Since for every obtained GPIO there will be one object of type struct GPIO descriptor, so it's better to create a variable of this structure type in the GPIO's private data structure. So that's why what I'm going to do now is I'm going to the private data of the GPIO device, and here I'm going to create struct GPIO descriptor, and I'm going to create a pointer variable to this. So that's why here dev data, dereference that and select descriptor is equal to this function, and here the first parameter is dev Next one is connection ID. Connection ID is born. Child's firmware handle. So we have got pointer to the device node, isn't it? Child. So child, dereference that firmware node. Okay, so you have to pass the address of this, and after that flags you can get from the consumer.h file. So here it is. I would like to go for this GPIOD as is, and after that the label. Anyway, you have the label here, so just use this dev underscore data label. Alright, so now let's check the return value of GPIOD underscore get function or its variants. So it returns the GPIO descriptor corresponding to the function connection ID of device dev. So it returns an error code called no entry if no GPIO has been assigned to the requested function, or any other error code. Okay, error code you must interpret using isError function. So that's why you have to check for the return value of this function in your program. Let's get back to the code. Let's check for this pointer. Okay, so you have to use isError. First let's check whether this is an error or not. So if it is true, then let's collect the error code. Okay, return is equal to, you have to use pointer to error code, and you have to mention this pointer here. So if this return value is equal to this error code, no entry error code, so minus no entry, so then we can print some message, no GPIO has been assigned to the requested function or index. Okay, so here just return the error code. So I hope you get this code block. We are just testing whether this is an error or not. So if it is true, then the error code is extracted using this macro, and if that error code is equal to no entry error code, then we just print that no GPIO has been assigned to the requested function and just return the error code. That means the probe has failed. So that's how you acquire the GPIO, and you get a reference to that GPIO in the form of pointer to a GPIO descriptor. We just learned how to acquire a GPIO, isn't it? Now let's understand some more kernel functions which are offered by the Linux GPIO subsystem. There is one more flavor of GPIOD underscore get function, that is get underscore index. This is used when the function is implemented by using several GPIOs together. For example, like this. Consider this GPIO property. So here one function, that is LED, is implemented by 3 GPIOs. So that's why its index is 0, its index is 1, its index is 2. To acquire this GPIO, you have to use this connection ID with this index. In that case, you can use GPIO get index. You can see that there is an index field. So in our case, we need not to use this because a function is realized using only one GPIO in our case. And now let's explore the GPIO manipulation APIs. So what do you do with GPIO lines? Why did you acquire a GPIO? You acquired a GPIO to manipulate that, right? You may want to set its direction like input or output. You may want to change its output state. You may want to read its input state, or you may want to configure the output type. A common output type of a GPIO pin could be a push-pull or open drain, or you may want to enable or disable a pull-up or pull-down resistors of a particular GPIO. So after acquiring a GPIO only, you can do all these activities. So now the kernel's GPIO subsystem gives you lots of kernel functions to achieve this. Now let's understand how to configure the direction for a GPIO pin. All these kernel functions you can explore from consumer.h header file. Consumer driver always should refer to the consumer.h header file. So for example, if you want to set the direction to input, so just use gpiod underscore direction input. That's it. You just mention the descriptor here which you acquired using gpiod get function. For the output you can use this. So gpiod direction output raw. So this means set the GPIO direction to output without regard for the active low status. As I said, a GPIO pin can have its hardware property like active low or active high. So when you use raw, then it doesn't matter whether its hardware property is active low or active high. Pin will be forced to the value what you mentioned here. So that's the meaning of raw. And there are some helper functions you can use to configure the flags of a GPIO pin. So now let's go back to the code, and after acquiring this GPIO, let's set the default direction for the detected GPIOs. So now I am going to set the GPIO direction to output. So for this I can use the function gpiod direction output. So this is actually there in the consumer.h, so you can explore that right here. Set the GPIO direction to output. So GPIO to set to output, so you have to mention the descriptor here and the initial output value of the GPIO. So value could be 0 or 1. You can read here, set the direction of the passed GPIO to output, such as gpiod set value can be called safely on it. The initial value of the output must be specified as the logical value of the GPIO, that is, taking its active low status into account. Alright, so if you are confused about this statement, you can consult the kernel documentation. You can go to the documentation gpio.txt. Here they have mentioned about GPIO's active high and active low usage. Let's understand this. It is natural to assume that a GPIO is active when its output signal is 1, that is high, and inactive when it is 0. However, in practice, the signal of a GPIO may be inverted before it reaches its destination, or a device could decide to have different conventions about what active means. Such decisions should be transparent to the device drivers. Therefore, it is possible to define a GPIO as being either active high or active low. When the GPIO is termed as active high, then 1 means active. When the GPIO is termed as active low, 0 means active. So that drivers only need to worry about the logical signal and not about what happens at the line level. So let me explain that. So GPIO's active high or active low scenarios you can understand with reference to something else. For example, let's say there is one device. I call it as some device. So let's say this is an SoC and this is a pin of the SoC which is controlling the device. So this is a GPIO pin. So now first let's understand what is active high. So active high or active low is from the perspective of the device which is being controlled. So in this case, for this device, active means 1, inactive means 0. That's why when you write 1 to this GPIO, that means when this GPIO's state becomes 1, it activates the device. Why? Because device active state is 1. This is defined by the device. That's why when the GPIO state becomes 1, it activates the device. When GPIO's level or state becomes 0, it deactivates the device. That is active high scenario. Now what about active low scenario? So in the active low scenario, active means 0 and inactive means 1. So that is what defined by the device. So usually it is represented at the device side by using a small bubble here. So this bubble signifies that this device is an active low device. That means when you write 0 into this GPIO, the GPIO activates the device. And when you write 1 to this GPIO, the GPIO deactivates the device. Here you can say that this GPIO is an active low GPIO. That means this GPIO is used for active low purposes because it is controlling a device which is active low in nature. I hope you get the idea about active low and active high. So active low and active high we discuss with respect to a device which is being controlled. So that's why what they say here is the initial value of the output, that is this value, must be specified as a logical value of the GPIO, that is taking its active low status into account. So let's say your GPIO is active low in nature and you mention this value as 1. Value as 1. And then what happens is this function inverts that value to 0. So you can see that inversion happens right here. If the GPIO is active low, then value is inverted. So like that, okay? Please keep this in mind. So that's why whenever you are controlling an active low GPIO, then you can activate that GPIO by writing 1 here. You need not to write 0, because if you write 1 here, then if it is active low, anyway it is inverted, isn't it? So that's why whenever you use this function, just remember that 1 means active and 0 means inactive. So it doesn't matter whether it is active low or active high. If it is active low, anyway the value will get inverted by this function, isn't it? So in our driver, now let's use this function to set the GPIO's direction to the output. I'm going to mention the descriptor, that is dev_data descriptor and the initial value, and I would like to mention 0, and it actually returns an error code. So if it is non-zero, then there must be some problem. So let's print it. Okay, I will just print and return the error code. So now let me save and exit. Let me just build this, and there seems to be some problem. So the error is because since we have already started using GPIO related functions, you have to include the consumer.h header file here. So include Linux GPIO consumer.h. So that's the only header file you require. Since I have used one return variable, so let me create one variable here, int return. Let's build this, and the build is fine. Okay, so complete up to here, and I'll see you in the next lecture. In the previous lecture, we understood how to acquire a GPIO, isn't it? Now in this lecture, let's continue with our exercise to create attributes. So we have to create three attributes: direction, value, and label. Direction is read write, value is read write, and label is read only. So I think by now you know how to create the attributes, isn't it? So now we have to create some attribute variables in our program, just like what we did for our earlier exercise. Now let's do this part. Okay, first we have to create three attribute variables, right? So let's do that. Let me go back to the device.h header file, and let's explore the macros what we used to create the attribute variable. So in the previous exercise, we actually used these macros, right? Device attribute, and we mentioned the name, mode, show method, and the store method. So in this exercise, instead of using this macro, we can straight away use these macros. You see here, this is a macro if you want to create an attribute whose mode is read and write. So this macro you can use to create an attribute whose mode is just read only. This is just for write only. So all you need to do is just mention the name of the attribute here. So it will create a variable of this structure type, that is struct device attribute type, and it will initialize the mode, it will initialize the show and store methods. If you look at the show method, okay, show method is formed like this. First the name is used, and then for that the keyword show is attached. That's how the name of the show method is formed. Same is true for the store method. Alright, so now let me just use these macros. Okay, let's go back to the exercise. So let me just paste that macro here. So static. So first let's create a read write device attribute variable. I would just call it as direction, and after that let's create two more, and so this is last one will be read only, that is for label. Okay, one is for direction and one is for value. That's great. So now let's implement the show and store methods. So if you don't know how to write a store method, if you forgot its syntax, then don't worry, go to the device attribute structure, and here is a prototype of show and store method. Just copy that and paste here. So need not to remember any prototypes. Okay, first let's implement the show method for the direction. First you should use this name, direction underscore show. So for a time being, let's just return 0. Okay, so later we can implement this direction store. So let me just copy paste these code block. So next is for value. This is for value, and so we have only show method for the label. Right, that's it. So in later lectures we will implement these show and store methods. By the way, there are few errors. Alright, so there are some errors. Now let's see why is that. Actually, you should create all these methods before this. Let's delete these variables and let me put here. So the methods should come before these variables. Now let's build this, and there are still some more errors. There are some problems, and after that this is direction show, direction store, value show and value store, sorry. So this must be value store, and after that label show. Okay, so that's fine. Now let's see, still some more errors. Alright, so these are some warnings of unused variables, so we'll see that later. Complete up to here, and I'll see you in the next lecture. Hey, welcome back to the lecture. So far we have completed these steps. The driver has created the Bone GPIOs class under sys class, that is over. And for every detected GPIO in the device tree, the driver should create a device under the created class, isn't it? This we haven't done, so in this video we are going to do this. And the third step is the driver should also create 3 sysfs files, right, attributes for every detected GPIO device. So we'll do these 2 steps in this lecture. Let's get back to the code, and now let's go back to the probe function, and in the probe function, after this step, here we have to create devices under sys class Bone GPIOs, okay, or whatever the class you just created. So how do you create a device? You use the function device create, isn't it? And once the device is created under that class, then what you do, you use sysfs related functions to create sysfs files, right? So but all these things can be done in one kernel function, and we are going to explore that kernel function in this video. So need not to first create the device and then use the sysfs functions to create sysfs files. For that, I would like to take you to device.h header file, and here just search for device underscore create, and here is a function device create. So you must be familiar with this function. So we have used it, device create, but for this exercise I don't want to use device create. Okay, that is another variant of device create, that is this one, device create with groups. So now let's explore what this does. Creates a device and registers it with sysfs. You see why I want to use this function is because of this. Additional attributes specified in the groups parameter will also be created automatically. That means, so whatever you did in the previous exercise using syscreate file, so that also can be done using this function. Here you just mention the class what you created and mention the parent, that means the detected GPIO device. You can mention the dev-t. So this dev-t is actually the device number. If this device number is non-zero, then what happens is the dev file will be created, which shows the dev tip for the device, isn't it? So the dev file actually shows the device number of this device that will be used by the udev to create device files in the /dev directory. For this exercise, we don't want to create any device files under root dev directory. Okay, why? Because this driver works only with the sysfs attributes. So you can just use sysfs attributes to change the property of the hardware, like you can change the mode, you can change the direction, you can write the values. After that, mention the device number here. We don't want to mention any device number here because we have no plans to create the device files under a root dev directory. If you mention 0 here, the dev file will not be created. Dev file will be created only if this field is non-zero. So that's why keep this argument 0. This field you can use it to mention the device private data. And after that, this is a place where you mention the name of your device which you are about to create. And look at this argument. So here you should hook up your attribute details. So if you do that, then this function will first create the device, and inside that device it will create all the attribute files. So now let's understand this argument. So what is this? Actually, it's a double pointer. You see here, this is a null terminated list of attribute groups to be created. So list of attribute groups. So now you have to create list of attribute groups in your program. I think I actually explained this structure in the previous exercise, where it has got this field where you should hook up the list of null terminated list of attributes. So first what we'll do is we'll create null terminated list of attributes. First we'll do that. So here first let's create null terminated list of attributes. How do you do that? So let's do static struct attributes. You should create a pointer array, right? So let me call it as GPIO ATTRS. Okay, a pointer array is equal to, first entry will be ampersand of this one, right? Device attribute, or what is that? Let's explore this macro again. So I forgot that. So device attr rew. Okay, so dev attr, right? So dev attr underscore the name is direction dot attr, right? Comma. So let's copy paste this. This is value and this is label. Okay, and it should be null terminated. All right, that's it. After that, let's create a structure variable for attribute group. Okay, attribute. So I think we did something similar in the previous exercise, right? Attribute group. So let me call it as GPIO attribute group is equal to, so here I should initialize only ATTRS field is equal to, you just hook up this, right? That's it. Now please note that you cannot use address of this here, you cannot use that. It's a double pointer. What this function says here, you see, it's a list of attribute groups. Now you should create a pointer array to store each attribute group. This is a little tricky, okay? You should create pointer array of attribute group. Static struct attribute group, a pointer array. So GPIO attribute, I'll just call it as groups or something like that, okay? So this must be a pointer array. And here you must first mention the address of each attribute group. So we have got only one attribute group, so that is this one, comma null. So it should be null terminated. So now you use this pointer here, okay? First we created variables, attribute variables, and after that we created list of attributes. This is list of individual attributes. List means pointer arrays. These are the individual pointers to these variables. And after that we created a group variable. This is a group variable which binds all these things under this variable. But I cannot use this group in that device create function. It demands list of groups. That's the reason I created list of groups. Again, another pointer array of this type. There is only one entry because we have got only one group. Like that you can create several groups and you can mention here. In one go, everything will be created under the sysfs by using this function. So it's a little tricky, okay? So if you just carefully analyze, then everything will start making sense. Now let's go to the probe function. So here let's use this function. First is class, after that parent is dev t is 0 because we don't want to create any dev file. Drivers data, this field we can use to store our device private data. Our device private data is dev data. So let's store that here, dev data, and groups. And this is for the attribute groups, and here to mention the list of attributes. So that is this one, okay? And after that device name you can mention here, okay? So string for the device name. So this is dev data of label, right? That's it. So this returns a pointer to struct device, right? Now to store the return value of this function, let me create one receiving pointer here. Struct device. So let me just create a pointer. So let me give the name dev sysfs, something like that. Dev underscore sysfs is equal to. Alright, so here you see actually it returns error to pointer on error. So now that's why you have to check this pointer using the macro isError. Alright, so we just finished implementing device create with groups, and I think that's the last step in the probe function. If you want more functionality, then we can always implement it later. But before ending this video, let me just summarize what we did in the probe function. First of all, our device tree has many child nodes, isn't it? So that's why we used a for loop here. For each available child of a node, for every iteration, child will be populated with the address of device node of a child here, and for every detected child, we first create a private data structure. So we first create a private data by allocating the memory, and after that this private data is populated by going through the device node entries. For example, in this code block, we update the label. We actually read the label property from the child node and we update that in the dev data. And after that, we acquire the GPIO, which is mentioned in the child node, by using its function name. The function name is bone. So this acquiring kernel function always returns a descriptor. So our descriptor is GPIO specific. For every acquired GPIO will have its own descriptor. So that's why descriptor is a GPIO specific. So that's the reason why I created the descriptor pointer in the GPIO's private data structure. And after that, this driver, always configures the initial direction of the acquired GPIO as output. I mean, you can even set for input, no problem. That is done here. And after that, we create a number of devices inside the class, what we created in the init function. And after that, we create number of devices in the sysfs, and this function also creates the device attributes. The device attributes are direction, value, and label. That's it for this lecture. We successfully implemented the probe, and in the next lecture, let's implement all these show and store methods, okay? And after that, we'll implement the remove function, and after that we can test this consumer driver. All right, now let me just build this project. There are a couple of issues. Let's fix that. First of all, here this is a label, and after that here this is ptr underscore error. There was a typo actually. So let's build again, and there is one more error. Here we are missing the const thing, okay? So what I want to do here is, so here this must be static const struct, okay? So that's what that function demands, okay? Right, that's it, okay? So it builds fine, no problem, and I'll see you in the next lecture. Hey, welcome back to the lecture. So in this lecture, let's implement the show and store methods for the attributes. So we have got 3 attributes here, and first let's implement direction show. In this method, we actually have to return the direction of the GPIO to the user space. So direction of the GPIO could be in input mode or it could be in output mode. So first we have to query the direction, and if the direction of the GPIO is in input mode, then we have to return a string in to the user, and if the direction of the GPIO is in output mode, then we have to return a string out to the user space. So basically this function presents a string value to the user, something similar to what we did in our previous exercise. In the previous exercise also, we actually returned a serial number of the device to the user space. So what we did there, actually we first extracted the device private data, and by using that device private data, we returned a string to the user space. So that's why I have first extracted the device private data from this pointer. Here I don't want to use dev parent because this pointer itself has a device private data which is being supplied during device create function. So let's go back to the device create function. Here it is. When you use this function, you mention the device private data here. So just take a look into this function, how it is implemented actually. So let's search for that device in the device.h. So here it is. So let's search for this. It calls this function, and you see here this driver data is initialized like this, dev set driver data. This function does that, so that's why it is not done in the pro function. Take a look into this line. So that's why I can use dev get driver data on this pointer to extract that device private data. After that, let's query the direction. Now for that, we can use a kernel function gpiod get direction. So just you have to pass the descriptor. So return the current direction of a GPIO. It returns 0 for output, 1 for input. Let's explore this function. So you have to visit consumer.h. Here it is, get direction, right here. Let's use this function. I'm just copying this. Alright, so let's create one variable dir. Dir is equal to dev data of a descriptor, and if dir is less than 0, then that's an error. So return dir. Otherwise, so if dir is equal to 0, then show out. If dir is equal to 1, then show in. Alright, so now let me create another variable here. Casta direction. So direction is equal to dir. Let me use conditional operator here. If dir is equal to 0, so if this is true, then we are going to store a string out, else otherwise it will be in. And after that, just use sprintf buff %s direction, right? That's how you submit the result. I hope that makes sense. And now let's go to direction store method. Alright, so now let's implement the store method for the direction attribute. Here you have to take the direction values from the user, right? So the user is going to send either in or out, and based on that you have to call appropriate GPIO configuration API to set the direction. For this purpose, you can either use GPIOD direction output or GPIOD direction input. If the user sends the string in, then you have to call this function. That actually configures the GPIO's direction to the input, otherwise output. For this output, function, you can mention optional value. In the store method, what I would do is, so the user's data will be in this buffer, isn't it? This buffer should contain either a string in or out. It should not contain any other values. There are only two possible values are allowed, that is in or out. So first you have to do a string comparison. So that means you have to use something like string compare with buffer and in. Let's say if it is true, then you can configure the direction to the input. But while dealing with sysfs files, okay, don't use string compare function. There is a different string comparison function which is offered by the kernel, especially for the sysfs files, okay. So we'll explore that. That is there in string.h. What you do is go to include, Linux string.h. Here it is. And here just search for sysfs string eq. Okay, right here. While dealing with sysfs attributes, okay, and if you want to do any string comparison, then it's better if you use sysfs underscore string equal function. So let's understand what this does. So it actually does a simple string comparison, but it has got some special feature. So return true if strings are equal, but it actually takes into account the trailing new line. So this routine returns true if two strings are equal, treating both null and new line then null as equivalent string terminations. It's geared for use with sysfs input strings, which generally terminate with new lines but are compared against values without new lines. Basically, when you are comparing two strings in which one string has got a new line termination and other string is without new line, in that case you can use this sysfs string equal function, because it treats both null and new line then null as equivalent string terminations. Because when user sends a string, let's say by using echo command, that string is actually new line then null terminated. I mean, it is also possible to use echo command not to send the new line character, but generally, when user uses the echo command adds a new line character into the string. So that's why this string comparison function takes that into account. That's why I'm going to use this function rather than simple string compare function. Right, so just use the if condition, sysfs string equal. So I'm going to compare the value of buffer with in. Alright, so if this is true, then I'm going to use this function, gpiod direction input. I'm just going to use this function. Here you just have to mention the descriptor. So descriptor I can obtain from the device private data. and it returns an error code actually. So if return is 0 in case of success, otherwise an error code. So let's catch the error code. So else if sysfs string equal an initial value, let's set it to 0. Else, I can say return is equal to invalid. So user has sent the invalid string. If return is non-zero, then just return ret, otherwise count. If return is 0, then count is returned. If it is an error code, then error code is written, or you can simply write like this. You need not to mention this. Alright, so now let's implement value show. So this value show actually applies to a GPIO which is either in input mode or in output mode. For this, you have to query the current state of a GPIO. For that, you can use the function gpiod get value, okay, right here. So returns GPIO's value. Return the GPIO's logical value, that is taking the active low status into account, or negative error on failure. So now let's use this function. First of all, we are returning number to the user in this function. Value show, value should be number. It could be either 0 or 1, right? So let's create one variable int value. So value is equal to gpiod get value dev data of descriptor s printf buff %d/n value. That's it. So that is our value show and value store. So user is going to send either 0 or 1 in the form of string. So you have to convert string to a number. So that's why you have to use a string to number conversion function, what we used in our previous exercise. Buff, let's use 0 here, and after that placeholder is long value. If return is non-zero, then it's an error. Otherwise you have to set the value for the GPIO. For that you can use gpiod set value. Right, so assign a GPIO's value. So you just have to pass the descriptor and the value. This function doesn't return anything, okay, it's void actually. So just return count here. After that, this is a label show method. So you just have to extract the label from the device private data and just return it and just write into the buffer. That's it. Alright, so that completes our implementation of attributes show and store methods. And now let me save and exit this, and let's just build this. Okay, so there are no errors. That's great. Complete up to here, and in the next lecture let's test this. Hey, welcome back to the lecture. So in this lecture, let's complete the remove function. So in the remove function, we have to call the device destroy. But implementing this remove method is a little tricky. So I'll explain you that. First of all, let's revisit our device create. Here it is. Here we are creating devices inside the sysfs. And after that, this function actually returns a pointer of type struct device. Actually we are losing that. So we are not storing that pointer which is returned by this function, because that pointers are really required in the remove function in order to execute a device destroy kind of thing. Because when the driver is getting removed from the system, or when the device is getting removed from the system, at that time this remove method will get called and you have to destroy the devices. So, or what you can call unbinding of devices. That's why let's create a placeholder to save the pointer returned by this function. This method is not useful. We have to modify our code. So that's why what I'm going to do now is I'm going to create one placeholder in the driver's private data structure. Here, let's create struct device a pointer array. Let's create a pointer array of type struct device. This array you can use to store pointers returned by the device create function. But if you write like this, then you have to mention size of this array. That becomes a static method. Otherwise, what you can do is you can declare this as a double pointer, and we can allocate memory for this dynamically in the pro function. In order to allocate the memory, we need to know how many child nodes are there in the device tree node. We have to get that information first so that we can allocate memory for this to hold number of pointers. That's why let me go to the for function. In the for function, before starting this for loop, I'm going to use this function in the of.h. of get child count. Let me create one variable, child count. Child count is equal to, let's use this. For this function, you just have to send the parent. Just send the parent device node. Actually, it returns child count. If child count is 0, then you can conclude it as devices found, something like that. So return E invalid, because you cannot proceed if the child count is 0. Or I can just write this as dev error. And after that, based on this child count, let's allocate the memory for the device variable what we just created in the driver's data structure. drv data dot dev is equal to devm kzalloc dev. Size would be size of struct device star into child count. So I'm creating space to store a pointer of this type for these many counts. That's why I'm reserving this much amount of memory. GFP kernel. After that, let's use this pointer to store a pointer which is returned by the device create. Let's go to the device create, which is right here. Let's remove this variable, drv data of dev of I hope you get this. Actually, we need not to create this child count variable. We already have a variable in driver's private data, that is drv data total devices. So we already have this. Let's use this total devices. So I'll just write total devices found is equal to, it is drv data total devices. And after that, when the remove function is called, you just have to loop. Let's say int I, for I is equal to 0, I is less than drv data total devices I++. So here you should call device destroy or something like that. Let's explore device destroy once again. I don't think I can use that. Device destroy. It is right here. In this case, you cannot use device destroy. It removes the device that was created with the device created. That's correct. You have to mention the dev.t, but we don't have dev.t. So during creation of devices, we mentioned dev.t as 0. If dev.t is 0, then you cannot use this. That doesn't make any sense. That's why we can use this device unregister straight away. So I'm going to use device unregister. Device unregister drv data dev of I. Remember that the remove function will get called only one time because we have only one device tree node, isn't it? Under that device tree node, we have more child nodes. Basically, we have only one device node. So that's why the remove function will get called only one time. You can send some messages here. So that's what we do in remove function. Let's save and exit. Let's just build this. It doesn't have any errors. And I think we have completed most of the things. Please note that here this case.lock should be outside this for loop. Don't put this inside this for loop. Here I think we did a couple of mistakes. First of all, this dev.sysfs we have to remove because we don't use that. Let's remove this variable. That's why here you should change this to drv disco data dot dev of I here too. So there are some more issues we have to solve. Here we remove the child count. That's why replace this with total devices. drv underscore data total devices. Let me save and exit and let's build this project. There are a couple of errors. Let's investigate this. Now let's check this. 134. Here we don't have dev, sorry. It is ampersand pdev of dev. And after that it is complaining about drv underscore data. Actually the variable name is not drv underscore data. It is gpio underscore drv underscore data. We have to change that in the remove function. Here this is gpio underscore drv underscore data, gpio underscore drv underscore data, and also let's see where and all we have used this here and here as well. So now let's save and exit. Let's build. That builds fine, no problem. And in the next lecture, let's test this. I'll see you in the next lecture. Hey, welcome back to the lecture. In this lecture, let's test this exercise on the target. Before testing, let's check our device tree file once again because we do the device instantiation from the device tree node. I think we have done one mistake there. I would like to recheck the device tree nodes what we created. Let's visit arch arm boot dts ldd course.dtsi. So here in the earlier videos, actually I wrote GPIO2 controller here. That is actually wrong because I checked the system reference manual, which is the updated one from the GitHub repository of beagleboard.org. Here, if you just go to the LED section, user LEDs. Here you see GPIO user LED 0 is GPIO 121. All LEDs are actually handled by the GPIO 1 controller. That's why please make that correction here. This node is for user LED 0, which is connected to GPIO 1.21. I have created two more nodes here. This is for the user LED 1 and this is for the user LED 2. GPIO 122, GPIO 123. Create these three device nodes because we can easily test our driver on these LEDs. That's why I have chosen these nodes. Let's save and exit this. And also open AM335X Bone common.dtsi. Here just search for LEDs. This is a LEDs block which is used by some other driver of the Linux. Basically it is used by GPIO LEDs driver. So the LED subsystem is already using these onboard LEDs actually. That's why for a time being let's disable these blocks. You can use status property to disable a node. I can use that instead of commenting this out. I can use status is equal to disable or something like that, but I'm not sure how the driver is written, whether it considers this status property or not. That's why instead of using the status property, let's comment this out. I'm going to comment out LD2, LD3 and LD4 blocks. So if you are wondering why I'm doing this, because since our driver is using these LEDs, you may not see the effect if it is used by some other driver of the Linux. So that's why I'm just disabling these device nodes. Let's save and exit. And we have modified our device tree file. We have to compile it and transfer to the target. Let's compile this. Make arch. So let's compile this. We got the device tree binary. Now let's transfer the DTB. And let's also transfer the driver. We first have to transfer this DTB to the boot directory. For that, we actually wrote a copy script. Let me just execute that. And after that, I have to reboot the machine. Reboot the BeagleBone. So you can just see that in the sys devices platform, you see now Bone GPIO devs. That's a new device node what we wrote. And now let's load the driver. In smart GPIO sysfs.ko. I think we did one mistake. Let's go back to the code. So we actually forgot to write the modules init and exit macros. So make sure that this IU keep outside this for loop. I'm going to remove this from here and let's keep that here. Right. So now let's do in smart GPIO sysfs.ko. So you see here the pro function of our driver gets called. So total devices found 6, and these are the labels of the detected device. First of all, let's try to remove this driver and let's try to reinsert to see whether there is any crash or not. Whenever you load any driver, first load it and unload it and then again try to load it. It should not cause any problems. I'm going to remove it, and here is a crash. So why is that? It says unable to handle kernel null pointer dereference. Go back to our driver. So I think we did one mistake in the GPIO sysfs exit. Actually, let's check our previous example, 006. In the exit function or in the cleanup function, we did platform unregister first and then class destroy. That was the correct method. I don't know why I did like that. So let me fix that. First, when the driver unregisters, it triggers the remove method. You remove all the devices and then you do a class destroy. That's the correct method. So I just transfer it, and here I have to reboot this now. Now let me try once again. GPIO sysfs, and let's try to remove this. Yes, it works. There is no crash now. And let's try to insert once again. Here you can see that these are the devices detected. Let's check that in sys class bone GPIOs. This is a new class created. Just do ls and these are the devices. Let's get inside one of these devices. Let me get inside this. User LED1 GPIO 1.22. Just do ls, and here you see these are your sysfs files, attributes which are created. So direction, label and value. Let's check the direction. It is out, label, value. All these values are actually returned by your store and show methods, what you have implemented in the driver. Let's just control the onboard LED by using these attributes. Please note that in your BeagleBone Black hardware, there are 4 user LEDs. These are the user LEDs. And here, the first LED is user LED 0. This is user LED 1, 2, 3, like that. I am now controlling user LED 1, that is this LED. Let's write the value 1 to the attribute value. It should turn on the user LED 1. Let's see that. On the board, the user LED 1 indeed turned on. Let's send 0 to it. It turned off. Even you can change the direction of the GPIO. Just send the string into direction attribute. And now let's try user LED 2. Can send echo 1 to value. Yes, it works. That's about handling GPIOs via the consumer driver, and we'll do more exercises with these GPIOs. In the next lecture, I'm going to cover the pin control subsystem, because you see in the device tree we have consumed a couple of GPIOs, but we haven't done any pad configurations for them. Luckily, the pad configuration was not required for this exercise because, as we know, by default the pin mode will be mode 7, that is the GPIO mode. That's why no pad configuration steps are required for this exercise. But if you are using a pin for some other purposes, like if you are using a pin for SPI communication or I2C communication or something like that, then pad configurations are really required. In the next lecture, let's see how to do the pad configurations for the IO pins. And after that, we'll do more exercises on this GPIOs. So I have one exercise where I show you how to connect the LCD to the BeagleBone Black hardware, and after that controlling that through the consumer driver. With that note, I would like to end this lecture, and in the next lecture, let's explore the pin control subsystem of Linux. I'll see you in the next lecture. Hey, welcome back to the lecture. In this lecture, let's understand the pin control subsystem of Linux. First of all, in the previous section, you understood that each pin has got multiple functionalities, what we call as modes, and the function